Okay, in our last video, we ended up with this formula for the variance of the sum of random variables. And there's this sum of variances plus 2 times the covariance. Now, in this special case, this is a very important special case, the special case where the random variables are independent, we have that the variance of the sum of independent random variables is the sum of the variances of independent random variables. And we can prove that quite easily because if you have independent random variables, remember what the covariance is. This is equal to the expectation of the product minus the product, that's xj, minus the product of the expectations. All right. Now, if they're independent, then the expectation of the product is equal to the product of the expectations. So we have the same term that we're subtracting and we get 0. Okay. Okay. Now, suppose you want the PDF for the sum of random variables. There is, in fact, a formula to find the PDF for the sum of continuous random variables. You have this formula. This is actually called this star is the convolution. Okay, it's not the product, it's the convolution. Sorry. These are the convolution. And I can prove this for 2 random variables. I'll show you on the other sheet. And let's show it for n equal 2. Whoops. Okay, so let's have y equal x1 plus x2. And what I want to, if I want the PDF, we can get that using the CDF. So I have fy of x, I can use x, is equal to the probability that y is less than or equal to x, which is equal to the probability that x1 is less than or equal to, x1 plus x2. Sorry, I did it again. x1 plus x2 less than or equal to x. And I can write that as the probability that x2 is less than or equal to little x minus big X1. Okay. Now I can think of this in terms of a region in space. All right. So let's see. I have my region. And here's x1 and x2. All right, now here I'm saying x1 plus x2 is less than, these are big x's by the way, x1 plus x2 is less than or equal to x. So if I have the sum, let's say that x is this value here. Okay, now x1 plus x2 less than or equal to x. In this case, if x2 equals 0, that's all of the part over here. Okay, now I can also say, have the point x here. That also satisfies x1 plus x2 less than or equal to x. And if I draw this line and consider all of the shaded region down here, all the shaded region below this line, the x1 plus x2 equals x line. Okay. Notice that for all of these points, for any point I choose here, this point here, whatever it is, call x prime, y prime, all these points satisfy the condition that x1 plus x2 is less than or equal to x. Okay? So to compute the probability that y is less than or equal to x, I need to integrate over this region in the x1, x2 plane. So to find the probability that y is less than x, and that's a little x, and this we must integrate. And what are we integrating? Well, we're integrating the joint density for x1 and x2. So we must integrate the density, which is little f, I can call that x1 comma x2, over the region shown. Okay, so let's do that. I want to integrate. Well, if you remember your integration here, you can see that x1 goes from minus infinity to infinity. And I'll put the dx1 here. Now the question is, what does x2 go from? Well, if you fix the x1, if this is x1 fixed, then what's this value? Well, that's the point where x2 plus x1 equals x. So this point must be x. Well, it's x1 plus x2 equals x. So this must be x minus x1. That's this point. And you're going down to minus infinity. So you're integrating from minus infinity to x minus x1. And then here you have f of x1, x2, x1, x2, dx2, dx1. Okay? Let me clean this up a little bit. Remember that these are big x's because these are the random variable. These are small x's. These are big x's here. All right? So I'm doing this integral. Now this is equal to the probability, and I should have it equals there. It's equal to the probability y is less than or equal to x. And that's the same thing as the CDF of y evaluated at x. Now we're asking for the PDF of y. The PDF of y is the derivative of the CDF. Okay, remember the CDF is the integral of the PDF, so the PDF is the derivative of the CDF. Okay. So it's equal to the derivative with respect to x of the integral from minus infinity to infinity, of the integral from minus infinity to x minus x1, little x's, f of x1, x2, x1, x2. And I'll just write dx2, dx1. Now you have to go back to your calculus. I can bring this derivative inside and apply it to this integral. Now, this integrand does not depend on little x. Only the upper limit of the integral depends on x. So let me write this as integral minus infinity to infinity. I think I know why this is slanted, because my board is slanted. I can bring the ddx inside, and here I have integral minus infinity to x minus x1. F of x1, x2, x1, x2, dx2, and then this is going to be dx1. Now here I wrote ddx. ddx is actually the same thing as d dx minus x1. Why? Because x1 is a constant, so that doesn't change the derivative. Now what do I have here? I have exactly the fundamental theorem of calculus. I'm taking the derivative of an integral, and the derivation variable is the same as the integration variable. The result when you take the derivative of an integral, so let's see, the fundamental theorem of calculus says that I'll write it with the same variable, d dx minus x1 of the integral from minus infinity to x minus x1 of, let me just call this g of x2, dx2, is going to simply be equal to g with x2 replaced by the integration limit. That's what the fundamental theorem of calculus tells you. Okay? You're not used to seeing it with x minus x1, but you're used to seeing it with x here and x here. These are just variables, so I can do it with any variable I want. Okay? So that's what I have here. I'm taking d parenthesis x minus x1 of this integral. The result is I take this integrand and I replace the x2 with x minus x1. So my result is that, let me repeat what I've got here, fy of x is equal to integral from minus infinity to infinity. You don't see it, but it's up there. And then in here what I have is the x2 replaced with x minus x1. So this is f big x1, big x2, x1, x minus x1, dx1. Okay. Now, so if x1 and x2 are independent, that means that f x1, x2, of, I'll just say AB, is equal to f x1 of A, f x2 of B. All right? So that's what I have here. So that means, so in this case, I'll have fy of x is equal to integral from minus infinity to infinity. I can break up this integrand into f x1 of x1 times f x2 x minus x1. And this is what's known as the convolution. And you write it as fx1 star fx2. Now, there is some intuition behind this formula. And you can consider it this way. Let me switch back to blue. Okay. Okay. Suppose I'm looking at x here, the value x, and suppose the random variable x1 is in this interval here. Okay. So I can say the probability that x1 is in this small interval, so I'll call this small interval, I'll call it little x1, x1 plus dx. Okay. That's going to be equal to the density times dx. Now, if x1 is in this interval, what's it going to take for x1 plus x2 to be x? Well, that means that x2 must take this value. So that means x2 would have to be equal to x minus x1. Okay, so here for x2 to be in that small value, we have probability of x2, big X2, equals x minus x1, which is equal to fx2 of x minus x1. So that's why why the x2 density of x minus x1 is multiplied by the x1 density at the point x1. Now I'm kind of sweeping under the rug this business about the dx's, but this is only supposed to give you some idea of why you pair the fx1 of x1 with the fx2 of x minus x1. Okay, so that kind of gives you an idea of the convolution formula, and that's how you find the sum. Let me make sure that he actually talked about the, he should have said that these are independent. So this is not true. It's only true if these are independent. So let me just make that very clear. Okay. But when they are independent, that's the very important case, because, like I said, statistics deals with lots of independent random variables. Okay.